8, and this is my presentation for Lab 4. In this lab, I analyzed a two-dimensional spring mass system. I compared theoretical data from a GlowScript v Python model with observed X and Y data from Tracker. I will show how the model follows the energy principle by plotting kinetic, gravitational, spring, and total energy. I used Tracker to collect the true positional data in GlowScript to generate the model predictions. The fundamental principles involved are Newton's second law, where the change in momentum equals net force, and the energy principle, where change in a system's energy equals the work done by the surroundings plus thermal transfer. My result is that the predicted motion closely matches the real motion, and the total energy stays essentially constant at zero, which supports the energy principle. For the model, I apply Newton's second law, written as force equals the time rate of change of momentum. I step the momentum forward using the update formulas. Position equals initial position plus velocity times time, and velocity equals initial velocity plus force over mass times time. These updates let me predict positions in GlowScript to compare to the video data. My assumptions are no friction is involved, no thermal losses are involved, and the mass behaves like a point particle. My system is the spring, the mass, and the earth. I treat the surroundings as empty for this model. I use the provided video and import it into Tracker to obtain the actual X and Y position data. For initial conditions, the system starts at rest. The mass is 0.402 kilograms. The initial position from Tracker is shown in vector form on the slide. Spring constant is 6.83 newtons per meter, and the relaxed length is 0.123 meters. My GlowScript program, which you can see on the right, sets up the scene with the mass attached to a spring under gravity. It creates graphs for X, Y, and the energy. It loads the Tracker data file and plots that data in red while the simulation runs in blue, so the comparison is visible. Each time step, the code updates momentum and position with gravity and spring force and computes kinetic, gravitational, spring, and total energy for plotting purposes. And here are the graphs that the code produced, and I'll discuss the results on the next slide. Looking at the energy plots, the potential energies oscillate as expected. When the spring is most stretched, spring potential energy is high and the gravitational potential energy is lower. As the mass rises, gravitational potential energy increases while spring potential energy decreases. Kinetic energy rises when the mass passes through the lowest point and falls near the turning points. When we add kinetic, gravitational, and spring energy, the total energy shows zero net change across the time. The position versus time graphs also indicate that the model is very accurate for X and slightly less accurate for Y, which matches what we see in the overlays. To answer the required questions, first, is the energy principle satisfied? My answer is yes. The change in total energy stays essentially constant at zero throughout the interval, which indicates that within the model and its assumptions, energy is conserved. Second, the oscillation periods from the data. From the X data, the period between peaks is roughly 1.6 seconds. From the Y data, it is roughly 1.5 seconds. The small difference is expected given tracking uncertainty and the fact that we did not include drag. The two estimates are close, which supports the overall consistency of the analysis. Overall, the theoretical model built on Newton's second law and the ideal spring force very closely reproduced the observed behavior. The energy exchanges behave as expected, and the total energy remains constant within small numerical issues. That is why I conclude that the energy principle holds for the system under the assumptions that we used. Thank you for listening.